Hey, this is Steven from LegitTechTutorials. Just make sure my mic is working because I unplugged it. So make sure it's working all the way. Hey, this is Steven from LegitTechTutorials, and welcome back to my product design or product development series. We are back working with the Smart Charger, the Smart Mixed Chemistry Battery Charger. And so this is just kind of like I think this is going to be a little bit shorter of a video. This is just an update of what I looked into and figured out that we need to do from a little bit of investigation, and how to basically wire up these digital potentiometers to take care of these analog potentiometers on this regulator board. So first things I did was I wanted to figure out which way these are orientated. As you see here, this is a picture of the one I bought, and you see these little screws here with my mouse here on the left side. That screw there, so that orientation there to figure out which side's like the specific side that you need to be on, that you need to wire the piece in order for it to sweep properly. And then I was in there looking more about the X9C104, the specific digital potentiometer that I got. And I found out that that digital potentiometer uses a 3-pin interface with the Arduino. And that I found through a little bit of searching here. As you see with these guys in a forum here. 5-volt in, VCC, ground, and then chip select, which is CS. I knew that was definitely one. An IO pin, any pin is IN or increment, or INC, which is an increment. Normally high, toggle this pin to change potentiometer pot wiper value. Then 2, this is just some particular pins that he's suggesting, probably for an Uno. To an IO pin, this is up down, high is up, low is down. I don't know exactly how that works, but I found that there is libraries that exist on the interwebs that work with this particular chipset, which is with this particular potentiometer, which is the X9C104. Now, there are a few issues that I found through further searching that might cause some problems, and we'll go into those now. And those problems come in between this potentiometer and this board, but we might be able to get around. It might be okay, so I'll talk about that right now. So so this is the company that makes it. Intrasil is the company that makes the digital potentiometer. It's a solid state SSD well, not solid state drive, but SS potentiometer, 100 wiper tap points. So basically, through quite a bit of looking through, basically that means exactly what you think it means. It means that between the lowest and the highest resistance value, there is 100. That's weird. There is 100. My router went out. There's 100 different subsections of the potentiometer cutup. So between its minimum value and maximum value, it is subdivided into 100 pieces. Now, the particular one that I purchased was the X9C104, which has 100 kilo ohm maximum resistance rating. And so the lowest resistance is 400 or something like that, 400 ohms, and it goes all the way up to 100 kilo ohms. And also that it works on 5 volts, which is good. And another thing that I learned here is that apparently the wiper position is stored in a memory on the chip that allows it during boot up to remember where that state was. I don't know if that's really relevant in our case. We really kind of just want to, we're going to start from So when we turn on the charge, it's going to start from start from minimum and then work its way up to the current that we're looking for. So it's always going to return back to normal, so we don't really care much about that. Yeah, so we have the X9 C104 100 kilo ohm, which is the largest rating. And I'll show you guys this here. I like this in more plain English. So it says, so yeah, this is talking about a use case of where you're using it for a testing machine or something, and then during the test, for example, if your test is using electronics, which generally most do, and you have resistors inside, resistors will change the resistance according to temperature, and these are temperature adjusted internally. So what you could do, these are adjusted for temperature and movement and stuff like that. So what he's saying there with that is the use case is that if you have resistors inside your circuit that are not adjusted, you could use this to adjust, to keep the resistance stable. So when those resistances change, you have this in series or in parallel to set that resistance to the correct resistance. Also, yeah, so temperature, humidity, and vibration will change resistance. So this will flatten it out. So yeah, right here, the digital potentiometer changes in steps of steps or increments, and the resistance is of a linear change, which I like that. I don't want to have the controller doing any sort of function guessing or whatever. For example, the resistance range of the X9 C104, which is the one that we have, is 40 R to, whoa, I thought this one's 100, now it's saying 1,000. So we're going to have to check that. We're going to have to check that out. Anyways, so I think that this is misspoken here, because here it says 100K, and then here it says 1,000K. So I don't know what the deal with that is. That's probably just a misprint. So it says divided up into 100 steps, so each increment is 1,000 R, right? Which that means that's 100K. So this is a misprint, right? Because 100 times that is 100K. So yeah, that's a misprint. So each point is 1,000 ohm resistance. So that's kind of like I don't know if that's going to be enough precision, but it will be good for this particular prototype. But it might be an issue as far as precision. So we'll see. Because that's not enough steps. Because quite a few of some other digital potentiometers are like 256 steps, right? But those also have an issue that this one's going to have, which I'll show you in a second. Yeah, so there's 100 steps, and then there's the interface. Chip select, up, down pin, and then increment pin. Resistance increase mode, linear change, working current 3 milliamps. Tabs will automatically store data when being off. This is the rate, blah, blah, blah. Okay. Yes. Okay, so now the issue. So the issue is that this is similar to the one I have. It looks almost exactly, but these three potentiometers are different. Now, what I looked into is I said, okay, is the digital potentiometer compatible with these analog potentiometers that are on this voltage regulator? So as you know, they have three. One is the CV, constant voltage, constant current, and the other one is under voltage protection, which we don't care about that. So, if you notice on top of those, they have numbers. So one says W204, the other one says W, and the other one says W504. So we're only worried about the one in the middle and the one on the right. The one on the left is under voltage. That will just be set and then never change. So the one in the middle says W204, and the one on the right says W504. Now, where you see that other thing where it says 0361, that is not the same on mine. So mine has from a different manufacturer, right? Actually, even I don't even have that same IC here. My IC is different also. This is a linear technology one. Anyways, so I figured out using my phone, because it's kind of hard to see. I figured out who manufactures this. It's a company called Bochin. Or Born. It looks like Bochin, but it might be Born. No, it is Bochin. Huh. I must Google the wrong one. Anyways. All is going up as Borns. Maybe they got acquired or something. Anyways. So this is the potentiometer that I have. It looks like that. And then what you find out is that the numbers on top are the sort of the layout of the particular potentiometer, and also the number of resistance here. So if you remember again, the middle one is 204, W204. W is the style, right? Model is a 3296, and also, by the way, why you didn't see this. Oh yeah, I went offline for whatever reason. Why you didn't see that is because it's on the front. It's on the front here, which you can't see from that image. So it says W204. W is the style. 3296 is the model of resistor. One, it doesn't say. This is here 1, 3 or whatever. Anyways. The main thing is the W204, and then it was W504. We're going to ignore the W, and then we're going to look down here at 204. 204 is, there's the issue, 200K. Now, our digital potentiometer can only hit 100K. So the question is that going to be an issue? And then how are we going to go about? Well, obviously the only way to solve that issue would be to buy a different potentiometer. So the other issues that most potentiometers that you could find are also very low on their max resistance. Most, from what I've seen going through Amazon really quick, 100K for these is the max that you're going to find very easily. So we might have to find some sort of custom, go hunting for a custom solution for this. And so it's not even big enough for the smallest one. And that's the constant current. The constant current one is the W204, which is a 200,000 ohms. Now the next one is the V out, which is the W504. W504 is 500,000 ohms. So basically we don't have enough resistance for these two guys, even the smallest one. This one is twice as much resistance, the other one's 5 times as much resistance as we're capable of. So on these we are, one, limited to how many steps we have, and then two, is that we're not even hitting the high enough resistance that the IC that the whole thing's rated for. Number one, it might be that these don't need to be that high; they just are for safety purposes. But that kind of doesn't really strike me because they're different. Two of these are W504s and one's 204, right? So there's obviously a requirement. And then going through EE98, which is Intro to Circuits this semester, I know sort of how these guys work on a simpler basis. and know that the resistance qualities of something that comes out of the out pin and also the adjust pin is very important in order to set the current or voltage to bias a load, or will bias a diode or some sort of load. So hopefully you don't use the entire 500,000. You don't use the 500 kilo ohm or the 200 kilo ohm, and it's just there for I don't know, it's just there. Because also if you go up and you see that the effective travel is 25 turns nominal. So if you have to go in here and turn it 25 turns, to get its full, so if you're in the middle, right, your middle, that's 12.5. 12.5 turns to the right and the left to get the precision that you want. That is obviously highly unpractical. So I don't know if they are even like practically going to be able to get that entire rotation. So I don't think that they had it to where it was supposed to use that entire resistance range. So hopefully 100 kilo ohm will work for both of these, because that's what I got. So that is the situation. So we figured out that that this might have a problem, and we figured out where these are coming from, and also on this page you figure out how it's wired. So so this is a little image that you have on the front of the potentiometer, and it says the wiper, and it says clockwise, counterclockwise. So what I'm going to assume is that from this this guy, my digital potentiometer, that that those pins would be like the right high, right low, and right wiper. So obviously the RW, the right wiper, is the number 2, and then the right high is, I'm going to guess that clockwise is increasing the resistance, right? I mean, I don't know if it says anything on here about, maybe it says 200 rotational life. Packaging. Yeah, so I'm gonna assume that clockwise is high and then counterclockwise is right low. So that means that we have those 3 pins. Also, it says on here what the 2 pieces, oh no, it says on here what the 2 pieces can be used for. This device can be used as a 3-terminal potentiometer or as a 2-terminal voltage resistor in a wide variety of applications. So in this case, we're trying to replace a 3-pin potentiometer, so that will work perfect for us. And we have 3 pins on the digital potentiometer that will go into the 3 pins of our physical potentiometer. So that being said, what we're using is we're actually using these 3 on this side. This is powered, so we don't have to worry about, we don't have to use this one or this one. We might, the ground is we're gonna have to have a common ground between here and here. So that way we don't have to use the ground. So we're gonna use this one, this one, this one, and then the voltage ground increment, up, down, and chip select are going to our Arduino. We'll pick some pins or whatever, but yeah. So let's just pick. Let's just do this really quick. Okay, so I put those away, did I? Oh, no. Some here. Okay, well, these are just some of the colors that I grabbed. So you got green, blue, purple. So we're going to probably reuse Oh, I already did one. Okay. Oh yeah, so I did do one. Here's the one I did right here. But of course it's done wrong. Right? This is ground we're not going to need. And these, let's redo them one at a time. So gray. Okay. So actually let's redo that. Let's do the purple one first. So obviously, as we know now, purple one's not going back to the board. Purple one's going up here. Oh, and I noticed that these don't have pins. So let's draw some pins on it really quick. 1, 2, 3, 1, 2, 3. And stroke is huge. Oops. There you go. And then go ahead and go back out. Objects, group. Alright. So with that, I'll go back and look at this guy and then figure out the orientation. Well, obviously, I don't have to do the orientation for the RW. RW is in the center. So, oopsies. I do need to zoom in a little bit. Okay. Okay. So there is RW. Next we're going to go R high, which is gray. Okay. And then okay, I'm looking at it. Okay, so it is, wait, where's the orientation? Oh, there it is. Okay, so saying clockwise on the right. And also, you'll see that clockwise, it doesn't say counterclockwise on here. It just says clockwise. So I'm going to assume that clockwise is high. It's increase. So, clockwise is on the interior, which is this right side. This right side here. Right? Yes. Because I'm looking on this other back side in here, and it says it's over here, so that's where it is. And I keep doing that. Gray. Oh, also I need to get rid of that. We don't need that. This is probably for like some sort of power setup. You're powering something as a 2-pin, right? You go in V and then ground. So that's probably your 2-pin resistor. It comes in and it comes out. So this probably has a resistive load rather than a 3-pin potentiometer. And then RL goes to that. And then basically identical to this bad boy down here goes up there to that piece. Yeah, so that is what I found out. so far with this guy, and where's my little wrapper? Oh, there it is. That's what I found out with these things so far. So hopefully those digital potentiometers work, and for the application that we're trying to do, and hopefully they serve us well. So again, still working on the room that I will be recording in. It's still under construction. So right now, physical projects kind of out of the question. So, you know, physical recording is still kind of out of the question. So next video I might try to do just some programming and stuff until we have the opportunity to use to do some physical recording, so we could do some software and some testing of this bad boy here. But yeah, stay busy, so find something to do, like I said, with the programming or something, and then do some physical recording. And the physical recording is going to be really fun to be able to do some soldering or something, or even some testing of this guy with a multimeter, see what's going on, and see if it works, and then maybe be able to read the wire something instead of these guys to see the resistance at each point, to see where we max in and out and something. But yeah, so if I run out of material, I will probably be swapping this temporarily until we're able to film more with this to a different RC project, which I'll probably be doing a video of either tonight or right now, or later on tomorrow. And like I said, that's for building a controller for tiny RC planes. And then, so if I run out of material for this guy, I will start doing that guy, and you'll see that series up. You'll see that season, quote unquote, season come up here soon. Well, that's pretty much all I wanted to do here in this video. Figured that out. That's the main thing that I was worried about, was the main control. That is the main control of pretty much everything, and then everything else is listening. So this is our only control point. Everything else is just feedback sensors. So now we have our control and feedback loops. So we could go about drawing a little bit more on the schematic of in and out and how that's going to work. But all that stuff's easy because it's just straight in, straight out. So power supply, straight in, straight out, pretty easy. You know, no libraries needed for that. And then out, when it comes out, it goes through the current sensor, and then goes to the voltage sensor, and then goes to the load, and then we test it on maybe like a heater or something, like a small heater or a Peltier cooler or something low current, and then see if we could set that current up and down, and then start doing some chemistry stuff with some intense settings of when to cut it off, and then also monitor each of the cells, etc., etc. That might be what we'll do in the next video, is lay out exactly what it needs to look like in the program for the final mixed chemistry, and also our testing schedule of each of those. And maybe we'll go back onto the Trello and say, okay, this is what we need to test, this is what we need to test, this one needs to be inside the program, this is the parts of the program that I need to implement in order for this guy to work. And then, so for example, for the testing, we have, test without digital potentiometers, test the resistance range, test the now with the digital and then test the digital potentiometers by themselves, going up and down on ranges, looking at it from the multimeter. Then we're definitely going to need to test the current sensor, the current and voltage sensor, so we know each of them work by themselves before we start putting pieces together. And then what we'll probably do is we'll do we'll do a combination of the voltage and current sensors, and then we'll just tell it to set an arbitrarily very low. We'll have something where you can control it from the touchscreen and have an arbitrarily low, or control it from the computer. Just type in what you want to set the resistance to. But we'll do an arbitrary low resistance, and then work our way up and make sure that the current actually ramps up, and then write that into code. And then we'll do the different code implementations up to the point where we do mixed chemistry, where you plug the battery in, it starts low, and it starts to build up to your current that you want to charge at. Charges. Monitors all the cells to each of the analog out pins, and then we'll shut the guy off, and then balance, and then charge up the low one through turn the input output pin to an out, from an in to an out for the cells, for the analogs. Turn them from an analog in to an out, and then feed it some current, and then charge up the low to the high. Pretty much. And that's what we're doing. And then at that point we would have built pretty much any sort of current, any sort of charger on the market for very expensive, but for $10 off pretty much, because most of the chargers that you would find that have a touchscreen are like $60, and I think I did about 40 on this particular project. Well, it depends at what this was. 21, yeah, so it was about $40. So already $20 off of any other touchscreen charger on the market at that point. And we get the bonus of we're charging the low instead of dissipating the high. So we always have that perfect 100% battery. And then at that point, anything else is just a bonus, right? Anything else is just a bonus. Alright, so this has been Steven from LegitTechTutorials. Thank you guys for watching. If you guys like this video, please subscribe for more videos like in this series and Earth series as well. I'll see you guys in the next video. Thanks for watching. Take it easy. Peace.